On the 11th of July 2026, a satellite passing over the Western Pacific photographed a stain on the ocean about 1,000 feet long. 5 days later, the United States Geological Survey raised the alert level on the volcano sitting underneath it. That volcano is American territory. Its summit stands 55 meters beneath the surface, close enough that the agency warned its activity could breach the open air, and then, 3 weeks ago, everything went quiet. No plumes, no signals, and the alert level never came down. Tonight we're going to work out what is actually happening down there, and why the answer depends on a microphone 1,400 miles away. Because the real question is not whether this volcano is erupting, it is how anybody would ever know. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and drop a comment and tell me where you're watching from tonight. Now let's get into it. Part 1. The Stain. On the Water. On the 11th of July 2026, a satellite passing over the Western Pacific photographed a stain on the ocean. It was about 1,000 feet long, 200 meters, end to end, a pale smear of discolored water sitting on an otherwise unremarkable stretch of sea, roughly 1,700 miles south of Japan. If you had been on a boat that morning, you might have sailed straight through it and thought nothing of it. Sediment, maybe. A trick of the light on a shallow bank. It was neither. That stain was the only visible evidence that something underneath it was awake. The water sits above a mountain. Not a metaphorical one, an actual mountain. A large conical volcano called Ahyi Seamount. And the reason you have almost certainly never heard of it is that its summit never breaks the surface. It stops 180 feet short. 55 meters of open Pacific stand between the top of that volcano and the air. Everything it does underwater, in the dark, with no ash cloud to photograph, and no lava fountain to film, and no village at its foot to evacuate. It helps to know what part of the planet we're standing on here, because this is not a random patch of sea. The Mariana Islands are the visible top edge of one of the most violent boundaries on Earth. The Pacific Plate is sliding westward and diving beneath the Philippine Sea Plate, and it does so along a trench that includes the deepest water anywhere on the planet. As that slab descends, it drags seawater down with it, locked into the minerals of the ocean floor. Deep beneath the arc, the heat and pressure squeeze that water back out, and water is the ingredient that makes rock melt at temperatures it would otherwise sit through unbothered. The melt rises. Where it reaches the surface, it builds volcanoes in a long curved chain. Most of that chain never gets high enough to become an island. For every peak in the Marianas with a name and a coastline, there are submerged cones sitting below the waterline, built by exactly the same process, doing exactly the same thing, invisible. Ahyi is one of those. It is not a geological oddity. It is a completely ordinary member of an arc that happens to have stopped 55 meters short of being a place. 5 days after that satellite image was taken, the United States Geological Survey raised the alert level on Ahyi Seamount to advisory and set its aviation color code to yellow. I want you to sit with the fact that this is an American volcano. Ahyi lies within the Commonwealth of the Northern Mariana Islands, which is United States territory. It has a US Geological Survey volcano number 284141. It has coordinates on file 20 degrees 26 minutes north, 145 degrees 1 minute east. It gets a weekly bulletin written about it by American scientists, published on an American government website in plain public view every single Friday. And as I am recording this, not one of those scientists can tell you whether it is erupting. That is not me being dramatic for the sake of an opening. That is the position the agency itself has published, in writing, in the same bulletins for years. I will read you the exact sentence in a moment, and once you have heard it, I do not think you will be able to unhear it. But start with the stain, because the stain is what the whole thing hangs on. First, though, understand what the survey actually did on the 16th of July, because those two words, advisory in yellow, are not decoration. They are the output of a formal system, and each of them means something specific. The volcano alert level runs in 4 steps. Normal is the baseline. The volcano is doing whatever it typically does. Advisory is the second rung, and its definition is that the volcano is showing signs of elevated unrest above its known background level. Above that sit watch and warning, which are the ones that get press conferences. Alongside that scale runs a separate colour code aimed specifically at aviation, and it runs green, yellow, orange, red. Yellow pairs with advisory. It is the aviation community's shorthand for a volcano that is stirring but not currently throwing anything into the sky. Now notice the strangeness of applying that second system here. The aviation colour code exists because volcanic ash destroys jet engines. Ash is fine, sharp, glassy rock dust, and when it goes through a turbine it melts on the hot section and resolidifies where the engine is cooler, coating the machinery in glass. There are aircraft flying today that once fell out of the sky, silently, for several minutes, because they flew through an ash cloud nobody had mapped. That system was built for volcanoes with summits in the air. Ahyi Seamount is 55 metres underwater. It has never put ash into a flight level in the modern record, and yet it carries a yellow aviation colour code because the survey judges that it might. That single administrative fact tells you how the agency is thinking about this mountain. You do not assign an aviation warning colour to a submarine volcano on the theory that it will stay submarine. When the survey described what that discoloured water probably was, they were careful. The plume, they wrote, along with other plume images from the preceding weeks, was likely the result of gas release into the water column. That is the observation. Gas coming up out of the seafloor into the sea in enough volume to change the colour of 200 metres of ocean and keep it changed long enough for a satellite to catch it on a pass. It is worth understanding why gas makes a patch of ocean visible from orbit at all, because the mechanism is not obvious and it matters later. What comes out of a volcanic vent on the seafloor is not just carbon dioxide and steam. It is a hot fluid loaded with dissolved metals and sulfur compounds, and the moment it hits cold, oxygenated seawater, chemistry happens fast. Sulfur comes out of solution as fine pale particles, iron oxidices and precipitates. The result is a suspension of extremely fine solids hanging in the upper water column, and fine suspended solids do one thing very reliably: they scatter light. Water that would otherwise absorb the red end of the spectrum and send back deep blue instead sends back a milky yellow-white or a rusty brown, depending on what is precipitating. So the stain is not the gas. The stain is what the gas leaves behind in the water on its way up, and the fact that it holds together as a coherent 200-metre patch tells you the supply from below was steady, not a single burp. Then came the interpretation, and the interpretation is where it gets strange. This activity, they wrote, could reflect vigorous hydrothermal degassing, or be associated with an ongoing effusive eruption. Read that again slowly. Those are two very different statements about the world. Vigorous hydrothermal degassing means seawater is circulating down through hot fractured rock, cooking, picking up dissolved gas, and venting back out. It means the system is hot and it is breathing. It does not necessarily mean magma is arriving anywhere. An ongoing effusive eruption means lava is coming out of the ground. It means molten rock is emerging onto the seafloor right now, being quenched by cold seawater, building the mountain a little taller. One of those is a plumbing system, the other is an eruption, and from where we are standing they look exactly the same. Then the survey wrote the line that should have made this a story that week, and did not because almost nobody was reading. In either case, they said, the observations indicate increased volcanic unrest and potential for activity to breach the ocean surface. Potential for activity to breach the ocean surface. That is a government agency saying, in the flattened language agencies use precisely so that they cannot be accused of hyperbole, that a volcano currently under 55 metres of Pacific Ocean might push what it is doing up through the water and into open air, not might grow slowly over centuries, might do it during the current episode of unrest. Now, I want to be scrupulously honest with you about the last month, because this story does not work if I oversell it, and the truth is stranger than the oversell anyway. In the two most recent weekly updates, the survey has reported nothing. On the 6th of August, nothing. And in the bulletin issued this morning, dated the 14th of August, 2026, at 2 minutes past 10 in the morning Chamorro Standard Time, the summary line reads, "No signs of unrest in satellite images or distal geophysical data this past week." The body of the report expands on it. No activity was observed in occasional clear satellite images or distal geophysical monitoring data over the past week, so the plumes stopped. The satellites see clean water, the distance sensors hear nothing, and the alert level is still advisory. The colour code is still yellow. Nobody has stood the volcano down. Why not? If there is no activity, why is the volcano still flagged? Here is where you need to notice something in the language. because the survey chose these words with care and they are doing a lot of work. Activity was not observed in occasional clear satellite images. Occasional and clear. The Northern Marianas sit in a part of the Western Pacific where cloud is the default condition, not the exception. The satellite is not watching the volcano. The satellite is passing over it sometimes, and when it passes over it, sometimes there is a hole in the weather, and that same bulletin, the one from this morning, the one that says no activity was observed, also contains this line about Ahyi's eruptive record. The most recent eruptive activity began in 2022. Began, not began, and ended. The survey has never published a date on which this thing stopped. So the question that this entire video is built around is not really, is Ahyi Seamount erupting? The question is sharper and considerably more uncomfortable than that. The question is, how would anyone know? Part 2. 55 meters. There is a number in this story that decides everything, and it is not the size of the plume or the date of the alert. It is 55 meters, 180 feet. That is the distance from the summit of Ahyi Seamount to the surface of the ocean, and if you want to understand why a submarine volcano nobody can see deserves your full attention, you have to understand what that number does to the physics. Start with the intuition most people have, which is that an underwater volcano is a safer volcano. The ocean is on top of it. Water puts fires out. Whatever the mountain does down there, the sea absorbs it. For deep volcanoes, that intuition is broadly right, and the reason is pressure. Every 10 meters of seawater you stack on top of something adds roughly 1 atmosphere of pressure to it. At 2,000 meters depth, which is where an enormous fraction of the planet's volcanism actually happens along the mid-ocean ridges, the confining pressure is around 200 atmospheres. Magma arriving at the seafloor under that kind of load simply cannot do the thing that makes volcanoes explosive. What makes a volcano explosive is gas. Magma at depth carries dissolved gas in it, mostly water vapor and carbon dioxide, held in solution by pressure the way carbonation is held in a sealed bottle. When the magma rises and the pressure drops, that gas wants to come out of solution and expand. If it expands fast enough and violently enough, it tears the magma apart into fragments, and that fragmentation is what turns a flow of molten rock into a blast of ash and pumice, moving at hundreds of miles an hour. 200 atmospheres of seawater keeps the cap on the bottle. The gas stays dissolved. The magma oozes out, chills against cold water, forms pillow lava, and builds the seafloor quietly. Deep submarine eruptions are, as a rule, effusive and contained. There are thousands of them happening across the planet at any given time, and none of them are anybody's problem. Now start walking that volcano upward. At 1,000 meters, the load is 100 atmospheres. Still enough. At 500, 50 atmospheres. Still, largely, enough. The behavior stays effusive. Lava emerges. The cold ocean strips heat out of its outer skin within seconds, and it forms the rounded tube-like lobes that geologists call pillows because that is exactly what they look like when you photograph them. Gas that would have expanded into a fountain in open air stays locked into the melt. Somewhere around 100 meters depth, the arithmetic turns. The confining pressure has dropped to roughly 10 atmospheres, and now the gas in the magma can expand fast enough to fragment it. The eruption stops oozing and starts blasting, and a second, separate mechanism switches on at the same time, and this one is arguably worse. When water meets molten rock in small quantities, it boils. When water meets molten rock in large quantities at the right ratio, with the two suddenly and violently mixed, it does not boil in any ordinary sense, it flashes. Liquid water converting to steam expands by roughly a factor of 1,700 at surface pressure, and if that conversion happens in milliseconds inside a mass of fragmenting magma, the result is not a plume of vapor, it is a detonation. The magma shatters the water into droplets. The water flashes and shatters the magma into finer particles, which exposes more hot surface to more water, which drives the process harder. It is a runaway. Volcanologists call this phreatomagmatic activity, and at shallow submarine depths it has a specific name taken from the place where the modern world first watched it happen from close range. In November of 1963, a fishing boat off the south coast of Iceland noticed smoke on the water, where no ship should have been burning. What the crew were actually looking at was a submarine eruption from a vent a little over 100 meters down, punching up through the sea. Over the following days, that eruption breached the surface, And then it kept going, building a cone of fragmented black rock out of the North Atlantic. It became an island. It was given a name, Surtsey, and it is still there. Scientists have spent the 6 decades since watching life colonize it. That is what happens when a shallow submarine volcano crosses the threshold. Not necessarily catastrophe. Sometimes the outcome is a new piece of land and an extraordinary natural laboratory. But the transition from a mountain that vents quietly into a mountain that throws material into the air is not a slow geological process taking millennia. At Surtsey, it took a matter of days from the first surface disturbance to open-air explosions. Ahyi's summit is at 55 meters. It is not near the threshold where that behavior begins. It is well inside it, by a factor of 2. And this is the point where the survey's phrasing stops sounding like bureaucratic hedging and starts sounding like a technically precise description of a real physical possibility. Potential for activity to breach the ocean surface. They are not speculating about the distant future. They are describing what a volcano with a summit at 55 meters, currently venting enough gas to stain 200 meters of ocean, is physically capable of doing. But there is a second half of the 55-meter number, and it is the half that I find genuinely difficult to stop thinking about. The volcano has not always been at 55 meters. The survey states it plainly in every bulletin. The summit has shallowed over the course of previous eruptions to 180 feet below sea level. Shallowed. Over the course of previous eruptions, every episode of activity at Ahyi has added material to the top of the mountain. Every eruption has built the summit a little higher into the water column. The volcano has been, slowly and across the observational record, climbing toward the surface. Think about what that means for the hazard, because it is not static. A volcano that erupts at 400 meters and then erupts again at 380 and then again at 300 is not repeating itself. It is walking up the pressure gradient. Each successive eruption happens under less confining load than the one before it. The same volume of magma with the same gas content produces a progressively more energetic result the shallower it gets, not because the magma changed, but because the lid got thinner. There is a nasty feedback buried in that too. A more energetic eruption fragments more material. Fragmented material is exactly what builds a cone upward fastest, because it piles rather than flows. So a volcano that is getting shallower tends to erupt more explosively, and erupting more explosively tends to make it shallower still. Nobody has demonstrated that loop running at Ahyi specifically, but the 2 ingredients it needs are both on the record: a summit that has shallowed across previous eruptions, and a current depth well inside the fragmentation regime. We do not have a clean historical depth series for this volcano. Nobody has been out there running repeat bathymetric surveys after every episode with the regularity that would let you draw that curve. But we have the survey's own summary statement, which is that the shallowing happened across previous eruptions, and we have the current figure, and we know that since 2022 there have been at least 3 separate periods of activity adding to the pile. There is one more thing about 55 meters that has nothing to do with magma and everything to do with people. 55 meters is not deep. It is roughly the depth of a moderately serious technical dive. It is shallower than the working depth of a lot of commercial fishing gear. It is well within the range where a large ship's hull and a shoaling seafloor start to have opinions about each other. And there is a hazard to a vessel above an active submarine vent that has nothing to do with hitting anything. A ship floats because the water beneath it is dense enough to hold it up. Fill that water with gas bubbles and its average density drops. A vigorous gas plume rising through the water column above a vent creates a region of aerated, frothy water that is measurably less buoyant than the ocean around it, and a hull that sails into it sits lower. Add hot water, floating rafts of pumice, acidic surface conditions, and the possibility of sudden steam bursts, and the water directly above a shallow erupting seamount becomes a genuinely bad place to be in a way that no chart symbol conveys. Which is why, tucked into the same bulletin, immediately after the description of the plume, there is a sentence that reads almost as an afterthought. Eruptive activity at Ahyi Seamount may present a hazard to mariners in the water, above and near the volcano. Mariners, in the water above the volcano. There is no exclusion zone out there. There is no buoy. There is no light, no horn, no marked hazard on the chart that updates when the alert level changes. There is a government website that publishes a bulletin on Fridays, and there is an open stretch of the Western Pacific with fishing boats and cargo traffic moving across it, and 55 meters beneath some of them, there is a mountain that the United States government currently classifies as being in a state of increased volcanic unrest. The people most likely to be directly above it when something happens are the people least likely to have read the bulletin, and in 1979, that is exactly who found out first. Part 3. The sentence, nobody reads. Every Friday, the United States Geological Survey publishes a document called the Northern Mariana Islands Weekly Update. It is not long. It is not written to be read by the public exactly, though it is entirely public. It is written the way a duty officer writes a log entry, in the flat declarative register of somebody who expects to be quoted back to themselves. Buried in the middle of it, in the section about Ahyi Seamount, there is a sentence that has appeared in essentially identical form for years. The lack of local real-time data means we are unable to forecast or warn of impending eruptions. I want to take that sentence apart because I think most people who skim past it do not register what has actually been said. This is not a scientist saying the problem is difficult. This is not a caveat about confidence intervals or model uncertainty, or the general humility that Earth scientists carry around about predicting anything. This is a specific, bounded, mechanical statement about capability. There is no local real-time data. Therefore there is no forecasting. Therefore there is no warning. Not poor warning, not short warning, no warning. And then, a few paragraphs further down, in the section describing how the whole island chain is watched, the survey says it again in a different way, and this time it applies the statement to every volcano in the territory, rather than just to Ahyi. This level of monitoring can detect significant volcanic activity in the Commonwealth of the Northern Mariana Islands, but cannot provide advanced warning of eruptions, detect, but not warn. Those two verbs are doing enormous work and they are not interchangeable. Detection is what happens after. Detection is the microphone at Wake Island picking up a signal that a room full of analysts eventually agrees was probably an eruption at or near Ahyi. Detection is a satellite catching a stain on the water on a clear pass. Detection tells you something happened. It is, in the most literal sense, history. Warning is what happens before. Warning is a seismometer on the flank of the mountain picking up the tremor that precedes an eruption by hours, sometimes by days. Warning is a tiltmeter registering the ground swelling as magma pushes into a shallow reservoir. Warning is a gas spectrometer, noticing that sulfur dioxide output has climbed by an order of magnitude over 3 days. Warning is what lets people move. It is worth being concrete about what those precursors actually look like, because the word forecast makes people imagine something mystical, and it is not mystical at all. When magma moves upward into a volcano, it has to break rock to make room. Breaking rock makes small earthquakes, and those earthquakes cluster in space and migrate as the intrusion advances, so a network watching them can literally track a body of melt moving through the crust. As the magma gets shallower, the character of the shaking changes. The sharp, brittle snapping of rock fracture gives way to a continuous humming called volcanic tremor, which is fluid and gas moving through cracks. The ground surface swells, sometimes by only a few centimeters, and instruments measure that swelling. Gas chemistry shifts as deeper magma, with a different dissolved load, arrives. None of this is a guarantee, and volcanoes routinely do all of it and then decline to erupt. But it is a signal, it is measurable, and at well-watched volcanoes it has repeatedly brought hours to days of notice. The Northern Marianas have the detection half of that. They do not have the warning half, and the agency responsible says so in writing weekly, without being asked. So what is actually out there? The survey lists it, and the list is short enough to read in a single breath. Northern Mariana Island volcanoes are monitored using seismoacoustic sensors on Saipan and by examining satellite imagery. We also use distant seismic stations in Guam and Chichijima, Japan, and hydroacoustic data from Wake Island, when available. 4 things. Let me put a distance on each of them, because the list reads very differently once you do. The seismoacoustic sensors on Saipan are roughly 550 to 600 kilometers south of Ahyi. That hyphenated word means the site pairs 2 kinds of instrument, a seismometer, which listens to the ground, and an infrasound sensor, which listens to the air at frequencies far below human hearing. Infrasound is genuinely powerful for volcano monitoring, because an explosion in open air pushes a pressure pulse that can be picked up hundreds of kilometers downwind and used to time and size the blast. Notice the problem though. Infrasound listens to the atmosphere. Ahyi Seamount does not currently touch the atmosphere. 55 meters of seawater is an extremely effective acoustic barrier between what the volcano is doing and what an air pressure sensor can hear, because sound crossing from water into air loses almost all of its energy at the boundary. The Saipan array would hear Ahyi clearly on the day it breached the surface. That is precisely the day you no longer need to be told. Saipan is also, and this is the part that matters, the population centre of the territory. That is why the instruments are there. They were not placed to watch Ahyi. They are simply the closest instruments that exist, by accident of where people live. The seismic stations at Guam are about 700 kilometers south. Guam is a different jurisdiction entirely, and those stations have their own reasons for existing. The seismic stations at Chichijima, Japan, are around 900 kilometers north. That is a foreign country's instrument network, contributing data to the monitoring of an American volcano, because there is nothing American any closer that can hear it. And the hydroacoustic data from Wake Island is 2,270 kilometers east, 1,410 miles. I am going to come back to Wake Island at length, because it deserves it, but hold the number. Now go back and read the last 3 words of that monitoring sentence again. When available. Not continuously, not in real time, when available. The single most sensitive detector of activity at Ahyi Seamount, the one that heard the 2022 episode start, the one that picked up the renewed signals in May of 2023, the one that has been the primary evidence for essentially everything we know about this volcano's recent behaviour, is described by the agency that relies on it with a conditional attached. I do not read that as negligence. I read it as somebody being scrupulously accurate about a piece of infrastructure they do not own, cannot task and cannot guarantee. Here is the comparison that makes the gap concrete. Think about how a well-instrumented volcano is watched. On somewhere like Kilauea, there are seismometers in a dense network across the edifice, continuously telemetering. There are tilt meters measuring ground deformation to microradians. There are global positioning stations tracking how the mountain inflates and deflates by millimeters. There are gas sensors sampling the plume composition. There are webcams. There are thermal cameras. When magma moves at Kilauea, the ground tells on it, in something very close to real time, and the observatory can watch an intrusion migrate through the rift zone hour by hour and say where it is going. That is not an exotic level of instrumentation. That is what monitoring a hazardous volcano in a populated area normally looks like. At Ahyi Seamount, the equivalent number is 0. There is no seismometer on the volcano. There is no pressure sensor moored above it. There is no ocean bottom instrument on its flank. There is nothing on the mountain at all. And the thing that makes this genuinely maddening rather than merely unfortunate is that the fix is not technologically hard. A single ocean bottom seismometer on the edifice would convert a 2,270 kilometer inference into a direct measurement. A moored hydrophone in the water column above the summit would hear the difference between a hydrothermal system breathing and magma arriving, and it would hear it immediately rather than after an analysis chain running through Tahiti. One instrument, not a network. One. I am not going to pretend the ocean makes this trivial. It does not. An instrument on the seafloor of the open Pacific is a hard engineering problem. It has to survive corrosion, pressure, storms, fishing gear, and its own battery life, and unless you run a cable to it or moor a surface buoy above it, it stores its data internally and tells you nothing until somebody sails back out and collects it. That is the difference between recording an eruption and knowing about one. A real-time capability at a site like Ahyi means either a cable, which is expensive over that distance, or a surface relay sitting in a typhoon corridor, which is a maintenance commitment rather than a purchase. But none of that is a mystery. Ocean bottom seismometers are deployed routinely, in fleets all over the world, for research campaigns that last months. Moored hydrophones sit in the Pacific right now. The gap at Ahyi is not waiting on an invention. That is a funding decision. Somebody, at some point, weighed a remote volcano with almost nobody living near it against a finite budget and made a choice, and the choice was defensible, and it produced the situation we are in now, which is that the United States has an active volcano it cannot see. Which raises the obvious question. If nothing is on it, and the nearest American instruments are 500 kilometers away, then what exactly has been listening to Ahyi Seamount all this time? The answer is that the ocean has. Part 4. The Silence. In August. Let me lay the last 2 months out in order. because the sequence matters more than any single date in it. Through the back half of June and into early July of 2026, satellites passing over the Northern Marianas picked up plumes of discolored water above Ahyi Seamount. Not one image. The survey refers to plume images in the last few weeks, plural, which tells you this was a persistent condition rather than a single event. On the 11th of July, one of those images caught the 1,000-foot plume that ended up in the bulletin. On the 16th of July, 5 days later, the alert level went to advisory and the aviation colour code went to yellow. Then, roughly 3 weeks of nothing in the public record. On the 6th of August, the weekly update reported no signs of unrest. And this morning, the 14th of August, the weekly update reported no signs of unrest again. No activity was observed in occasional clear satellite images or distal geophysical monitoring data over the past week. The alert level did not move. It is still advisory. The colour code is still yellow. There are exactly 2 ways to read that sequence, and I want to give you both of them properly, because I think most coverage of stories like this picks one and pretends the other does not exist. The first reading is the boring one, and it is probably correct. Ahyi had an episode of elevated unrest in June and July. The episode wound down, the venting slowed, the plumes stopped, and what we are watching now is the tail end of a volcano going quiet. The alert level is still elevated because agencies are conservative about downgrading, and because a fortnight is not very long, and because it costs nothing to leave a remote seamount at advisory for another few weeks while you make sure. Under this reading, the story ends with a bulletin in September that quietly moves Ahyi back to normal and green, and nobody notices that either. The second reading is the one that keeps me up. Under the second reading, nothing has changed at the volcano at all. What changed is the observing conditions. Go back to the exact phrasing in this morning's bulletin. Activity was not observed in occasional clear satellite images. Occasional and clear. Take those 2 words one at a time, because each of them is describing a separate limitation, and together they are describing a very thin thread of observation. Occasional is about orbits. The satellites that can resolve a 200-metre feature on the ocean surface are in low polar orbits, a few hundred kilometres up, circling the planet roughly every hour and a half while the Earth turns underneath them. Any given spacecraft passes over a specific patch of tropical ocean at most a couple of times a day, and for optical imaging it needs the daylight pass, not the night one. There are geostationary weather satellites parked over the Pacific that stare at the same hemisphere continuously and update every few minutes, but they sit 36,000 kilometres out and their pixels are kilometres across. A 200-metre discoloration does not exist as far as they are concerned. The instruments with the resolution to see the plume are the ones that only glance, and the instruments that never look away cannot see it. Clear is about weather, and the weather here is not neutral. The Northern Mariana Islands sit in the deep tropical Western Pacific, in the part of the planet with the warmest open ocean anywhere. Warm ocean means convection, and convection means cloud, towering, persistent, and regenerating daily. The monsoon trough migrates through these latitudes in the northern summer, and this is August, in the Western Pacific, which is the most active tropical cyclone basin on Earth, and August is the heart of its season. Cloud there is not an occasional inconvenience, it is the ambient state of the sky for large fractions of the year, so the number of genuinely usable looks at a specific patch of ocean out there over the course of a week can be very small. Sometimes it is one, sometimes it is none. And a satellite pass that returns a solid white image of cloud top does not appear in the bulletin as a failure. It appears as part of a week in which no activity was observed. The other half of the sentence has a technical term in it that most people slide past. Distal geophysical monitoring data. Distal simply means distant, and the survey is using it precisely. Every geophysical instrument feeding this assessment is somewhere else. Not a bad instrument, not a broken one, a distant one. When the bulletin says nothing was observed in distal geophysical data, it is reporting that a set of sensors between 500 and 2,200 kilometers away did not register anything they could attribute to this volcano. So when the bulletin says no activity was observed, it is telling you the truth, and the truth is compatible with 2 entirely different worlds. In one, the volcano is quiet. In the other, the volcano is doing something and nobody got a clear look. And now layer the physics on top of that, because this is where the second reading gets its teeth. What actually produces the satellite signature? Gas. Enough gas, venting vigorously enough, to discolor a patch of ocean 200 meters across and hold that discoloration long enough to be caught on a pass. That is a fairly specific and fairly energetic thing for a volcano to be doing. An effusive eruption does not necessarily do that. Lava emerging onto the seafloor at 55 meters depth, quenching against seawater, building the summit, that process can proceed with gas output well below the threshold that stains the surface. It would produce essentially no optical signature at all. You could have magma coming out of the ground at Ahyi right now, and the satellite would see clean blue water, and the bulletin would say exactly what it says. There is also the matter of what the ocean does to the evidence. A stain on the surface is not a permanent feature. Currents move it, wind mixes it, and the fine particles that make it visible eventually disperse or sink. The plume in the 11th of July image existed as a coherent object because it was being continuously resupplied from below. Reduce the supply modestly, and the ocean erases the signature within hours. The difference between a visible plume and no plume at all is not necessarily the difference between erupting and not erupting. It can be the difference between two rates of the same process. What about the acoustic side? Would Wake Island not hear it? Sometimes, not always. The hydroacoustic detections that established the 2022 episode were of signals consistent with an undersea volcanic source, which in practice means impulsive events and tremor, the sounds of fragmentation, of explosions, of gas and rock moving abruptly. A slow, effusive flow is a much quieter thing. Lava extruding onto the seafloor and chilling is not a percussive process. It does not generate the sharp, energetic transients that survive 1,400 miles of ocean and still stand out above the background of ship traffic, weather, marine life, and every other earthquake happening in the Pacific that day. And the data is available when available. So here is where we actually stand, stated as plainly as I can manage. There is no observation currently in existence that distinguishes between a volcano that has gone quiet and a volcano that is erupting quietly. Both worlds produce the same bulletin. Both worlds produce clean satellite images and silent distant sensors. The evidence does not discriminate. That is not a failure of interpretation. Nobody is being slow or careless. It is a structural property of watching a mountain from 600 kilometers away with an instrument that was put somewhere else for other reasons. We have run into this exact failure mode before on this channel, and recently. In our video from late July on the Aleutian Arc, one of the details that stuck with me was how much of the monitoring problem at Atka came down to weather. Clouds sitting below 10,000 feet for days at a time, defeating satellite observation of a volcano that was actively venting. Same physics, same blind spot, different ocean. There is one more piece of language in this morning's bulletin that I have not been able to let go of. In the standing description of Ahyi's eruptive history, the last line reads, "The most recent eruptive activity began in 2022. Began, not occurred from 2022 to 2023, not took place in 2022 and again in 2023 and 2024. Began in 2022, and then the sentence stops." I have read a lot of these bulletins now, and I do not think that is sloppy writing. I think it is precise writing about an imprecise situation. The survey has never been in a position to state that the episode which started in October of 2022 has ended, because ending is not something you can observe from 2,270 kilometers away. You can observe that you have stopped hearing things. That is not the same as observing that the thing has stopped. 4 years, one open sentence, and the entire evidentiary foundation underneath it, every detection, every date, every confirmation that this volcano did anything at all, comes from a microphone sitting on a coral atoll 1,400 miles to the east. Part 5. A microphone 1,400 miles away. Wake Island is a coral atoll in the middle of nowhere. That is not a slight, it is a description. It sits in the North Pacific roughly 2,000 miles west of Hawaii and about the same distance east of the Philippines. A triangle of coral barely 9 feet above sea level at its highest natural point, with an airstrip laid across it and a small population of contractors and personnel. It has been a refueling stop, a battlefield, a missile test site, and a listening post. What it has never been is close to anything. It is 2,270 kilometers from Ahyi Seamount, 1,410 miles, and in the middle of October 2022, the hydroacoustic sensors at Wake Island started hearing something. It is worth knowing what a hydroacoustic station actually is, because the word sensor makes people picture a device bolted to a pier, and that is not what this is. A station of this kind is a set of hydrophones, underwater microphones, suspended deep in the water column, well below the surface, hanging at the depth where the ocean carries sound best. They are anchored to the seafloor, held up by flotation, and connected back to a shore facility by cable, so the data arrives continuously, rather than sitting in a memory card until somebody comes to get it. They are not deployed singly. A station is typically a small group of hydrophones separated by a few kilometers, and that separation is the entire trick. When a sound arrives, it reaches one hydrophone slightly before the others, and from those fractions of a second of difference, you can compute the direction the sound came from. One instrument tells you something happened. A cluster tells you which way to look. The signals were consistent with activity from an undersea volcanic source. That is the careful phrasing, and it is careful for a reason. What arrives at a hydrophone 1,400 miles from an event is not a recording of that event. It is a heavily filtered, dispersed, smeared acoustic signature that has travelled through a medium that changes its properties with depth, temperature and salinity along the entire path. You do not listen to it and say that is a volcano. You analyse it and say this is consistent with an undersea volcanic source, and then you go looking for corroboration. Consider the travel time, because it makes the scale of this tangible in a way that the distance in kilometres does not. Sound moves through seawater at roughly 1,500 metres per second. Over 2,270 kilometres, that is about 25 minutes. When something happens at Ahyi Seamount, the noise of it spends 25 minutes crossing the Pacific before any instrument in the monitoring chain registers that anything occurred at all. Not 25 minutes of processing, 25 minutes of the sound simply being in transit, moving through cold black water while the volcano does whatever it is doing. The corroboration process is the part of this story that I think is genuinely remarkable, and also the part that makes the underlying problem impossible to look away from. To confirm that what Wake Island was hearing was Ahyi Seamount, the survey worked with the Laboratoire de Géophysique in Tahiti, French Polynesia. Then the combined analysis brought in seismic data from stations at Guam and from Chichijima Island in Japan. There is a reason it took that many parties, and it comes back to what a single station can and cannot resolve. A hydrophone cluster gives you a direction. From Wake Island, that direction is a line running west into an enormous amount of ocean, and there are a great many things along that line capable of making a noise. Other seamounts, ordinary undersea earthquakes, and the general acoustic clutter of a working ocean. A bearing is not a location. To turn a bearing into a position, you need a second independent constraint that intersects the first, and preferably a third to confirm the intersection. That is what the seismic stations at Guam and at Chichijima provided. Energy from the same events arriving through the ground rather than through the water, from two very different directions, 700 kilometres to the south and 900 kilometres to the north. Cross those constraints and the ambiguity collapses onto a small region of seafloor. Do the work carefully enough, with a laboratory that specialises in exactly this kind of long-range acoustic analysis, and you can state a conclusion. Sit with the geography of that for a second. To establish that an American volcano was erupting, in American territory, under American jurisdiction, it took hydroacoustic data from an atoll 1,400 miles away, a geophysics laboratory in French Polynesia, seismic stations in a separate American territory 700 kilometres south, and seismic stations belonging to Japan 900 kilometres north. 4 datasets, 3 countries, an ocean's width of instruments, triangulating on a mountain that nobody could see, and it worked. The combined analysis confirmed the source was at or near Ahyi Seamount. That episode ran from October of 2022 through May of 2023. Roughly 8 months. Then came a sequence that I think is the cleanest illustration in the entire file of how this volcano is actually observed, and it happened across about half a day in May of 2023. On the 21st of May, at about 10 minutes past 10 in the evening Chamorro Standard Time, which is 10 minutes past 12 in the afternoon Universal Time, the underwater pressure sensors at Wake Island began registering signals consistent with eruptive activity at Ahyi again. Not a single impulse. Signals, beginning at that time, which is the phrasing you use for the start of something ongoing. Roughly 12.5 hours later, at 43 minutes past 10 on the morning of the 22nd, Chamorro time, a satellite passed over the Northern Marianas and imaged a plume, of discolored seawater above the area of the previously active vent. I want you to notice the order of those two observations, because I think it is the single, most quietly revealing detail in this entire story. The ocean heard it first. The satellite confirmed it the following morning, and notice what had to happen in between. The volcano had to keep going. Whatever restarted at Ahyi on the evening of the 21st had to sustain itself through the night, vigorously enough to keep pushing gas into the water column, so that by the time an imaging satellite happened to be overhead in daylight, there was still a stain on the surface for it to catch. Had the episode been 6 hours long instead of at least 12, there would be no satellite image in the record at all. There would only be an acoustic signal from an atoll 1,400 miles away, and a note that it was consistent with an undersea volcanic source. The primary detection instrument for an American volcano is not a camera, and it is not on the volcano. It is a microphone on a coral atoll 1,400 miles away, and the thing that looks down from orbit is the follow-up. Now, I have been describing Wake Island as a microphone, and that is close enough for the purposes of this story, but it undersells what is actually there and where it came from. The hydroacoustic infrastructure in that part of the Pacific has a long lineage, and a lot of that lineage is military. The physics that lets you hear a volcano from 1,400 miles away is exactly the physics that lets you hear a submarine. And during the Cold War, an enormous amount of money and engineering went into building networks that could do precisely that across ocean basins. Some of what exists in the Pacific today descends from that effort. Some of it was built for treaty verification, listening for the acoustic signature of nuclear tests, which is a monitoring problem with the same shape. A rare, energetic, deliberately concealed event somewhere in an ocean, which you have to detect, locate, and characterize from thousands of kilometers away, using nothing but the sound it made. That heritage is the reason the capability exists at all. Nobody would have built an ocean basin acoustic surveillance network to study volcanoes. The volcanology is a beneficiary of infrastructure that was funded for entirely different reasons, which is a recurring pattern in this field and is usually a good news story. This is, incidentally, where a certain kind of internet theory usually enters the conversation, and I will deal with it properly later, because the factual kernel underneath it is real, even though the conclusion people draw is wrong. But here is the operational consequence, and it is the reason the survey writes the words when available. The Wake Island arrays are not a volcano monitoring instrument. They are infrastructure that exists for other purposes, that happens to be extraordinarily good at hearing undersea volcanism, and that the survey draws on when the data is there to be drawn on. Nobody at the survey can task it. Nobody can point it at Ahyi. There is no dial. It is a resource that is sometimes available, and when it is available, it is the best thing anybody has by an enormous margin, and when it is not available, then the entire detection capability for this volcano falls back to a satellite, looking for a stain on the ocean through a hole in the clouds. That is the system. That is what has produced every single thing we know about this mountain's behavior in the modern era. Which leaves one obvious question hanging, and it is a question about physics rather than politics. How does a mountain 1,400 miles away make a sound that anything can hear at all? At that distance, across open ocean, sound should be gone, spread out, absorbed, lost in the noise of a planet's worth of water. It is not gone. And the reason is that the ocean has a structure in it that almost nobody outside the field knows exists. Part 6. The Ocean's Sound Corridor. Sound does not travel through seawater at a single speed. The speed depends on temperature, on pressure, and to a lesser degree on salinity, and those three things vary with depth in ways that pull in opposite directions. Near the surface, the water is warm, and warm water carries sound fast. As you descend, the temperature drops, and the speed of sound drops with it. Keep descending and eventually the temperature stops falling much. The deep ocean is uniformly cold, but the pressure keeps climbing, and pressure pushes the speed of sound back up. So there is a depth where sound travels slower than it does anywhere above or below, a minimum. In the mid-latitudes it sits at roughly 1 kilometer down, and depending on where you are on the planet and what time of year it is, the layer occupies somewhere in the range of 300 meters to 4 kilometers of the water column. That minimum is called the sound fixing and ranging channel. Everybody calls it the SOFAR channel. What makes it extraordinary is what happens to sound that enters it. A sound wave travelling within that layer that starts to drift upward moves into warmer, faster water, and refraction bends it back down. A wave that drifts downward moves into higher pressure, faster water, and refraction bends it back up. The layer traps acoustic energy between two invisible ceilings and will not let it escape. Sound in the SOFAR channel does not spread out into 3 dimensions and dissipate the way sound normally does. It is corralled into a horizontal corridor and forced to travel sideways. The result is that low-frequency sound entering that channel can propagate for thousands of kilometers before it fades. The ocean is not an obstacle to hearing a distant volcano. The ocean is the instrument. This was worked out in the 1940s, and the first application anybody built with it was a rescue system. The idea was that a downed airman in the open ocean could drop a small explosive charge set to detonate at channel depth, and listening stations on distant coastlines would pick up the sound and, by comparing arrival times, work out where in an entire ocean he was floating. A signal from a device you could hold in one hand, heard across a basin, resolved to a position. That was the original demonstration that the corridor was real and that it worked at scale. The specific signals that come out of submarine eruptions and earthquakes have a name. They're called T-waves, or tertiary waves, and they form when seismic energy travelling through rock reaches the seafloor and converts into acoustic energy in the water. Once converted, that energy finds the sound channel and rides it. T-waves are the reason regions of the planet with essentially no conventional seismic coverage, which is to say most of the ocean floor, are not completely invisible. For a sense of what these things are capable of, when the Monowai volcanic system erupted underwater in 2011, T-phases from that eruption were carried through the SOFAR channel more than 15,000 kilometers. 15,000! That is a third of the way around the planet from one submarine volcano through water. Against a number like that, Wake Island hearing Ahyi from 1,400 miles stops sounding impressive and starts sounding almost trivial. Of course it can hear it. The ocean is built to carry that sound, and that in the end is the trap this whole story sits inside. Because the sound channel works so well, and because it carries eruption signals across entire ocean basins to instruments that already exist for other reasons, there has never been an urgent operational case for putting anything on Ahyi Seamount itself. Why spend money mooring a hydrophone above a remote summit when the Pacific will deliver the signal to a receiver you already have? The answer is the one the survey publishes every Friday. Because a signal that arrives after the fact, filtered through 1,400 miles of water and an analysis chain running through Tahiti, tells you that something happened. It cannot tell you that something is about to. The ocean is a superb historian. It is a useless early warning system. And the first time anybody documented Ahyi Seamount doing anything at all, there was no instrument involved whatsoever. There was a boat and a crew and water that came up smelling wrong. Part 7. 1979. The first entry in the modern record of Ahyi Seamount is not a waveform. It is a story told by fishermen. In 1979, the crew of a fishing boat working the water above the summit area felt shocks. Then they watched sulphur-bearing water come up around them. That is the whole of it, as the survey records it, one sentence in the standing history section of every bulletin. But I have thought about that sentence a great deal while putting this together, and I would like to slow it down, because there is a lot inside it. Start with the question of why anybody was there at all. A boat in the open Western Pacific, hundreds of miles from the nearest sizable port, does not end up above a specific submarine summit by chance, as often as you might think. Seamounts are where the fish are, and the reason is fluid dynamics. A conical mountain rising off the seafloor forces the deep ocean current to go around and over it, and that deflection drags cold, nutrient-rich water up from below into the sunlit layer. Nutrients plus light produce plankton. Plankton produce small fish. Small fish produce tuna. Fishing crews across the Pacific have known for generations that the water above an undersea peak is worth working, and modern charts mark seamounts precisely because they are productive ground. So the crew were not lost. They were doing exactly what you would do. They had positioned themselves over the most productive water in that stretch of ocean, which is another way of saying they had positioned themselves directly above an active volcano, because the same mountain does both jobs. Then felt shocks. A boat is not a seismometer. The ocean absorbs and diffuses ground motion, and a hull floating on top of moving water is one of the worst possible places to notice an earthquake. Energy arriving from the seafloor has to cross into the water column, travel up, and then couple into a floating object that is already being moved constantly by swell. For a crew to feel shocks through a deck, the events underneath them had to be substantial and close, and repeated enough that nobody wrote it off as a wave hitting the hull wrong. There is a name for this in the maritime record. Mariners have reported what old logs call sea quakes for as long as there have been logs, a sensation described consistently as the vessel shuddering as though it had run aground in open water, sometimes hard enough to knock objects off shelves. It is an unmistakable and deeply wrong sensation, because a boat that shakes without a wave hitting it is a boat responding to something that has no business being in the water at all. Then the water, sulfur-bearing water, upwelling. If you have ever been near a volcanic hot spring or a fumarole field, you know exactly what that means at the level of the senses. Hydrogen sulfide has a smell that is impossible to mistake and impossible to ignore, and it arrives with a physical quality. It does not drift toward you so much as replace the air. And it has a property that makes it genuinely dangerous rather than merely unpleasant, which is that it disables your ability to detect it. At low concentration, it is overpowering. At higher concentration, it deadens the olfactory nerve within a few minutes, and the smell simply goes away. A crew standing on a deck in a rising gas plume would experience the stench vanishing, and would reasonably conclude that the episode had passed. That is the opposite of what the disappearance means, so picture the scene properly. Open water, no land in sight, hundreds of miles from help, in an era with no satellite phone and no position beacon. The deck shudders underfoot, repeatedly. The sea around the hull turns, discolored water welling up from beneath, and the air fills with a smell like rotten eggs that then, unnervingly, fades. There is nothing to see. Whatever is happening in the dark 55 meters down, and the only interface between it and them is the hull they are standing on. They were floating directly on top of an erupting volcano, and they found out the way a person would have found out in the year 1800. Now here is why that matters for this story rather than being merely a good sea tale. Everything we know about what Ahyi did in 1979, we know because someone happened to be there, not because a monitoring system caught it, not because an alert triggered. There was no analysis, no confirmation chain, no bulletin. A boat was in the wrong patch of ocean at the right moment. The crew reported what they experienced, and that report is now a permanent line in the official volcanic record of the United States. Think about how much had to go right for even that much to survive. The crew had to survive it and get home. Somebody aboard had to consider the event unusual enough to describe to someone ashore rather than filing it under strange things that happen at sea. That description had to reach a person who recognized what it implied, and who knew that global volcano catalogues accept and record eyewitness reports of exactly this kind. Then it had to be written down against the right mountain out of all the mountains under that ocean. Any one of those links failing, and 1979 is not in the record. The volcano still erupted. We simply would not have the sentence. Turn that around and the implication is immediate and uncomfortable. How many other times did Ahyi do something in the decades before and after, with nobody floating above it? The honest answer is that nobody knows, and nobody can know. The record of this volcano before instrumental detection is not a record of what the volcano did. It is a record of when the volcano and a human being happened to occupy the same square mile of the Pacific at the same time. There is a temptation to file 1979 under quaint history, the bad old days before we had proper instruments, before satellites and hydrophone arrays and international analysis collaborations. And it is true that the detection method has changed completely. In 1979, it was a nose and a pair of legs on a moving deck. In 2022, it was a hydroacoustic array in a laboratory in Tahiti. But look at what has not changed. In 1979, we found out because something happened to be in the right place. In 2026, we find out because a satellite happens to pass at the right moment through a hole in the clouds, or because an array that exists for other reasons happens to be recording when the sound arrives. The instruments got vastly better. The dependence on happening to be there did not go away. It just moved 1,400 miles offshore and up into orbit. And 22 years after those fishermen smelled sulfur, that dependence produced the single strangest detection in this volcano's file. Part 8. Heard from French Polynesia. On the 24th and 25th of April 2001, Ahyi Seamount had an explosive submarine eruption. We know this because of a seismic station on Rangiroa Atoll. Rangiroa is in the Tuamotu archipelago in French Polynesia. It is roughly 7,000 kilometers from Ahyi Seamount. To put that in terms that might land better, that is further than New York to Rome. It is most of the way across the Pacific Ocean. An American volcano erupted explosively for 2 days, and the detection came from a station in French territory on the other side of the world's largest ocean. Pause on what that requires of the event itself. Anything detectable at 7,000 kilometers has to have been energetic. The signal has to be strong enough at the source to still be distinguishable, after crossing an ocean, from the constant background of a planet that is always making noise, earthquakes on every margin, shipping, storms, the sea itself. Analysts working that kind of data are not fishing a whisper out of silence. They are looking for something that stands up above a permanently noisy floor, which means the 2001 event was not a modest gas release. It was explosive, sustained across 2 days, and loud in the specific sense that matters here. It delivered abrupt high-energy pulses into the water column, repeatedly, of the kind that convert efficiently into acoustic energy and survive the crossing. And here is the asymmetry that should bother you. The events big enough to be heard from 7,000 kilometers are heard. Everything below that threshold is not merely poorly characterized, it is absent. The catalogue is not a record of Ahyi's behavior. It is a record of Ahyi's loudest behavior, filtered by distance. Now, the survey is careful about how it describes what that detection could actually resolve, and the caveat is the part I keep coming back to. The event was well constrained, they write, to plus or minus 9 miles, 15 kilometers, at a location near the southern base of Ahyi. And then this. The summit of the seamount lies within the location uncertainty. Read that carefully. The best available location for the 2001 eruption is a circle with a radius of about 9 miles sitting near the base of the volcano. The summit is inside that circle, but so is a lot of other seafloor. Work out how much. A circle with a radius of 15 kilometers encloses roughly 700 square kilometers of ocean floor. That is an area comfortably larger than many cities. Ahyi itself, as a cone rising from the seabed, occupies a footprint that is a small fraction of that circle. The uncertainty ellipse is bigger than the volcano, which means that even the sentence Ahyi Seamount erupted in April 2001 is doing some quiet work. What can actually be said is that an explosive submarine eruption occurred somewhere in a region that contains Ahyi Seamount, and Ahyi is overwhelmingly the most likely candidate because it is the large active volcano sitting in the middle of the circle. That is a strong inference. It is not a measurement. I do not say that to cast doubt on it. The inference is almost certainly right, and I would bet heavily on it. I say it because it is a clean illustration of what remote detection actually delivers. From 7,000 kilometers, you can establish that something explosive happened, and roughly when and roughly where within about 9 miles. You cannot establish which vent, or how big, or how long the individual explosions lasted, or whether the summit changed shape, or whether anything failed on a flank. Everything that would matter for understanding the hazard is below the resolution of the measurement, and then consider what came next, which is nothing. After April 2001, the record of Ahyi Seamount goes quiet for 13 years. The next documented episode is 2014. There are 2 ways to read a 13-year gap, and by now you can probably supply both of them yourself. Either the volcano genuinely rested for 13 years, which is entirely plausible for a system like this, or it did things during those years that were smaller than the detection threshold of an era whose best available instrument for this purpose was a seismometer on an atoll 7,000 kilometers away. Nothing in the record distinguishes those. The gap is not evidence of quiet. The gap is the shape of what we could hear. There is one more thing about 2001 that I think gets lost, and it has to do with when anybody actually knew. An eruption located from 7,000 kilometers away is not a live event to the people analyzing it. Seismic data from a remote station goes into an archive. Somebody works through that archive, identifies an unusual signal, characterizes it, computes a location with its uncertainty, and publishes the result. That process does not happen in an afternoon. By the time the sentence "an explosive submarine eruption occurred at Ahyi Seamount on the 24th and 25th of April" exists as a statement anybody can read, the eruption has been over for a long time. There was no alert level on Ahyi in April 2001. There was no aviation color code, no advisory, no weekly bulletin flagging elevated unrest, because there was no mechanism by which anyone could have known in the moment that anything was happening. Whatever vessels were working that stretch of the Western Pacific during those 2 days were working above an explosively erupting volcano, and the only reason we can say that now is that a station in the Tuamotus recorded a signal that somebody eventually got around to examining. 25 years later, the survey publishes a color code for this volcano every Friday. That is real progress, and I do not want to be glib about it. But the underlying situation the colour code describes has not changed nearly as much as the existence of the colour code implies. And notice, again, the pattern this fits into. 1979, detected by a fishing boat that happened to be overhead. 2001, detected by a seismic station in French Polynesia that happened to be listening in the right frequency band, 7,000 kilometres away, and located to a precision coarser than the mountain itself. 2022, detected by hydroacoustic sensors at Wake Island, 1,400 miles east, and confirmed only by combining that data with a Tahitian laboratory's analysis and seismic stations in Guam and Japan. 3 episodes, spread across more than 40 years, each detected by an instrument that was not there to watch this volcano, from a distance measured in thousands of kilometres after the fact. In 2001, the nearest instrument that mattered was on the other side of the Pacific. In 2026, the nearest instrument that matters is still 1,400 miles away. That is the entire arc of progress at this volcano over a quarter of a century. The distance came down. It never came close. And then, in 2014, we got the first episode where anybody was able to see what the eruption had actually done to the mountain, and what it had done was open a wound down one side of it. Part 9. The Crater and the Chute. The 2014 eruption at Ahyi Seamount ran from the 24th of April to the 17th of May, 23 days. It was detected the way these things are detected, using seismometers positioned on the sub-aerial volcanoes elsewhere in the Northern Mariana Islands and the hydrophone arrays at Wake Island. The usual arrangement, instruments far away, listening. But 2014 has a detail that none of the other episodes have, and it is the reason this part exists. NOAA divers were in the water. They were not there for the volcano. They were conducting coral reef research near Farallon de Pajaros, the island 18 kilometres northwest of Ahyi. And while they were down there working, they heard explosions. Consider what it takes for that to happen. Sound moves through water more than 4 times faster than it moves through air, and it carries very much further because water is dense and does not absorb acoustic energy the way the atmosphere does. A diver underwater is effectively inside the medium that carries the signal, with their skull in direct acoustic contact with it. 18 kilometres is nothing to a low-frequency pulse in seawater. It is a distance the ocean crosses in about 12 seconds. So the divers were not straining to catch something faint. They were working in the water, and there were detonations in it, arriving from beyond the visible range, distinct enough that trained people in the middle of a completely unrelated task recognized them for what they were. I find that image hard to shake. A research team doing reef survey work, and underneath the ordinary sounds of a reef, the sound of a volcano detonating 11 miles away, arriving through the water clearly enough that human beings identified it without instruments. 35 years after fishermen felt the deck shake, the detection method had come full circle. People in the water hearing it happen. But the part of 2014 that actually matters for the hazard is what the eruption left behind, and this is where the story stops being about monitoring and starts being about the shape of the mountain. 2 things changed at Ahyi during those 23 days. The first is that a new crater formed near the summit. That is what an explosive submarine eruption at shallow depth does. It excavates. Material that was part of the edifice got blown out of it, and a hole was left where the vent had been working. The second is the one I want to spend real time on. A large landslide chute developed on the southeast flank of the volcano. Let me unpack what those words describe, because chute is a mild-sounding word for what it is. A submarine volcano like Ahyi is a cone. It is built by successive eruptions piling material outward and upward, and the material it is built from is not solid coherent rock in the way a granite mountain is solid. It is a heap of fragmented volcanic debris, lava that quenched fast and shattered, ash, blocks, loosely consolidated material stacked at whatever angle it happened to come to rest at. There is a limit to how steeply loose material can stack before gravity takes it back, and that limit, the angle of repose, sits somewhere around 30 to 35 degrees for dry rubble. Underwater, cones frequently stand steeper than that, because water buoyancy reduces the effective weight of the grains, and because a chilled crust of quenched lava can hold a slope together like a shell. That extra steepness is borrowed, not earned. It depends on the crust staying intact and on nothing shaking the pile hard enough to break the delicate contacts between grains. That is a structure with a standing tendency to fail. Add water saturation, add repeated shaking from eruptions and volcanic earthquakes, add the constant loading of new material dumped on top, and flank failure is not an exotic outcome. It is a normal part of how these mountains live. Ocean floor mapping around volcanic islands worldwide routinely finds enormous debris fields spread across the seabed around them. The remains of flanks that let go, at scales far beyond anything witnessed in recorded history. A landslide chute is the scar left when a mass of that material lets go and runs downslope. It is a channel gouged into the flank. It is evidence that a section of the volcano detached and travelled. That happened at Ahyi, on the southeast side, in 2014. It is in the official record, and then two things follow from it that nobody has resolved. The first is that a flank which has already failed once is not thereby made safe. Often the opposite. Failure removes support from the material upslope of the scar and leaves an oversteepened headwall, which is precisely the geometry that tends to fail again. A chute is also a prepared pathway. The next mass to let go on that side has somewhere ready-made to run. The second is that since 2014, Ahyi has had at least 3 further periods of eruptive activity. The 8-month episode from 2022 into 2023, the episode from December 2023 into April 2024, and whatever has been happening this year. Every one of those episodes was adding material to a volcano that already has a failure surface cut down one side of it. And here is the thing that closes the loop back to everything we have been talking about. Nobody knows what that flank looks like now. There has been no detailed public resurvey of the southeast flank of Ahyi Seamount since the 2014 chute formed. Establishing whether it has been reloaded, and by how much, and whether the headwall has steepened, would require a bathymetric survey, a ship running multi-beam sonar in overlapping lines across the volcano, mapping the seafloor in 3 dimensions, then comparing that map against the previous one to find where material has been added and where it has gone. That is not exotic technology. Research vessels do it constantly, but it means ship time, and ship time in that part of the Pacific means days of transit each way from the nearest port that can support such a vessel, in a typhoon basin, for a survey of a mountain with no population anywhere near it. On any reasonable ranking of what a research ship should be doing with a 2-week window, Ahyi does not obviously come first, so it has not happened, or if it has, the results are not in the public record. So we know the flank failed because the 2014 episode happened to get studied. We do not know its current state because nobody has been back to look, which means the single measurement that would convert flank failure at Ahyi from a plausible mechanism into a quantified risk simply does not exist. We ran into a version of this problem earlier this month in our video on Mount Rainier. Different volcano, different ocean, entirely different setting, but the same underlying question about a mountain whose interior strength has been quietly compromised, and the same recognition that the thing determining the hazard is the material condition of the edifice rather than the eruption itself. At Rainier, at least, people can walk on it. Part 10. The episode that never ended. I want to put the modern eruptive record of Ahyi Seamount in one place, because seen as a list it says something that no individual episode says on its own. 1979. Felt and observed from a boat. Duration unknown because the only instrument present was a crew who eventually sailed away. April 24th to 25th, 2001. Explosive submarine eruption detected from French Polynesia. 2 days, or at least 2 days of activity loud enough to cross an ocean. April 24th to May 17th, 2014. Detected by regional seismometers and Wake Island hydrophones, heard by divers. New Summit Crater, Southeast Flank Landslide Chute, 23 days, October 2022 to May 2023. Detected by Wake Island hydroacoustics, confirmed with Tahiti, Guam and Chichijima. Roughly 8 months, December 2023 to April 2024. Submarine plumes and geophysical detections at Wake Island. Roughly 5 months, June and July 2026. Plumes, alert raised to advisory on the 16th of July. Ongoing status unknown. 6 documented episodes across 47 years. Now look at the durations in sequence. 2 days, 23 days, 8 months, 5 months, and look at the spacing between the recent ones. The 2022 episode ended, as far as anybody could tell, in May of 2023. The next one started in December of 2023. 7 months of gap between an 8-month episode and a 5-month episode. That gap has a technical name, the repose interval, the quiet time between eruptive episodes, and it is one of the standard things volcanologists watch. because it is a rough proxy for how a system is being fed. A volcano with long repose intervals is generally one where magma accumulates slowly and erupts rarely. Short repose intervals between long episodes suggest something closer to a system, with a steady supply arriving from below, spending most of its time in some state of activity and only briefly resting. If you take the recent series at face value, it describes a volcano that has shifted from occasional brief explosive events to long sustained periods of activity separated by short pauses. A mountain that used to erupt and now, more or less, is erupting, with intermissions. I have to be disciplined here, because that reading has a serious problem in it, and I would rather raise the objection myself than let it sit unexamined. The problem is that the record is not a record of the volcano. It is a record of our ability to detect the volcano, and that ability has changed enormously across the exact period in question. In 1979, there was no detection capability at all beyond human presence. In 2001, remote seismic detection could catch an explosive event of sufficient size from 7,000 kilometers, but only an explosive one, and only a large one. By 2014, regional seismometers and the Wake Island arrays were both contributing. By 2022, there was a working analysis collaboration spanning 3 countries, and satellite imaging over the intervening decades had improved in every dimension that matters here: resolution, revisit frequency, spectral range, and the sheer number of spacecraft in orbit taking pictures of the ocean. So of course the recent episodes look longer and more frequent. We can now hear things we previously could not hear, and see things we previously could not see. A volcano that had been quietly effusing for months in 1990 would have produced no record whatsoever. The same behaviour in 2022 produces an 8-month entry in the official history. There is a second, subtler distortion sitting on top of that one. The duration of an episode is not measured. It is inferred from the span between the first detection and the last. Push the detection threshold down, and both ends of that span move outward. You catch the quiet beginning you would previously have missed, and you keep hearing the quiet tail you would previously have lost. The episode gets longer in the catalogue without anything changing at the volcano. This is one of the most common errors in this entire field, and it is worth naming plainly because it turns up constantly in discussions about whether volcanic or seismic activity is increasing globally. More detections of a constant phenomenon look identical to an increase in the phenomenon. Detection networks densify, catalogues fill in, and the graph goes up while the Earth does exactly what it was already doing. If you want a clean test of whether that is what you're looking at, ask whether the increase is concentrated in the small events, which is what improved sensitivity produces, or spread evenly across all sizes, which is what a real change produces. At Ahyi there are 6 episodes in half a century. That is nowhere near enough to run that test on. So the honest position on the duration trend is unproven, and probably at least partly an artifact. But there is one element of the record that is not vulnerable to that objection at all, and it is the one that matters most. The shallowing is physical. The summit has shallowed over the course of previous eruptions to 55 meters below sea level. That is not a statement about detection capability. That is a statement about the height of a mountain. Whatever else is or is not true about the frequency and duration of Ahyi's eruptions, material has been added to its summit, repeatedly, and the top of the volcano is now closer to the surface of the ocean than it used to be. And think about the volume that implies. To raise the summit region of a cone by any measurable amount, you cannot just drape a thin skin over it. You have to build a body of material with a footprint wide enough to support the new height. Every meter of shallowing represents a genuinely large quantity of rock delivered from below, distributed across the top of the edifice, and left there. Whatever has been happening at Ahyi across the observational era, it has been productive. We do not have the depth series that would let me put a number on it, and I am not going to invent one. But the direction is not in dispute, because the agency that monitors the volcano states it as a plain fact in every bulletin it writes. Better instruments do not make a mountain taller. That one is real. There is also a definitional problem underneath this whole list, and it is worth surfacing because it changes how much weight the list can carry. What is an eruptive episode at a volcano nobody can observe directly? At a land volcano, the answer is reasonably concrete. You can watch material come out of a vent, and you can watch it stop. You can put a date on the first lava and a date on the last, and photographs exist for both. At Ahyi, an episode is defined by the boundaries of a detection. the day the distant instruments started registering signals they could attribute to this source, and the day they stopped. Those are dates about the monitoring system. They are only indirectly dates about the mountain. So when the catalogue says the 2022 episode lasted roughly 8 months, the honest translation is that for roughly 8 months, an array 1,400 miles away kept picking up things consistent with this volcano. What was happening on either side of that window is unknown, and what was happening during it, whether it was continuous or a dozen separate pulses with quiet stretches between them that nobody could resolve, is also unknown. Take that seriously in the 2022 to 2023 episode, the December 2023 to April 2024 episode, and the 2026 unrest stop looking like 3 separate events with gaps between them. They start looking like 3 windows during which somebody happened to be able to hear a system that has been in some state of activity throughout. The survey's own phrasing points in that direction, not 3 episodes, but eruptive activity that began in 2022. That is a much less dramatic claim than saying the volcano has been erupting for 4 years straight. It is also considerably harder to argue with, which brings us to the sentence I flagged at the very start, and which I think reads differently now than it did at the beginning. In this morning's bulletin, in the standing description of Ahyi's history, the survey writes, "The most recent eruptive activity began in 2022. No end date. 4 years, and the sentence has never been closed." I do not think that is an oversight, and I do not think it is a claim that the volcano has been continuously erupting since 2022. I think it is the most precise thing the survey is in a position to write. To say an eruptive episode ended, you need to be able to observe absence, to be confident that the reason you are hearing nothing is that there is nothing to hear, rather than that you are not in a position to hear it. From 2,270 kilometers, through an array that is available when it is available, under a sky that is clear occasionally, absence is not observable. An open entry like that has a strange downstream effect too. Every statistic anybody computes about this volcano, average episode length, time between eruptions, proportion of the last decade spent active, depends on a start date and an end date. Ahyi's most recent entry has only one of those. Any number you calculate from it is provisional, and will stay provisional until somebody's in a position to write down a day on which this stopped. So the sentence stays open, and the alert level stays at advisory. And Ahyi is not even the volcano in this territory with the worst monitoring problem. It is the one with the best. Part 11. The 10 with no alert level. At the bottom of every Northern Mariana Islands weekly update there is a list, and the first time I read it properly, I had to read it twice. Due to a lack of geophysical monitoring on any of the volcanic islands, the survey writes, the following volcanoes have alert levels of unassigned. Then the names, Anatahan, Saragan, Farallon de Pajaros, Supply Reef, Maug, Asuncion, Agrigan, Pagan, Almagan, Guguan, 10 volcanoes. Understand what unassigned means because it is not one of the alert levels. The system runs normal, advisory, watch, warning, green, yellow, orange, red. Unassigned is not a low reading on that scale. It is the absence of the scale. It means no determination has been made, and no determination can be made because there is nothing on the mountain to make it with. That distinction is not academic. An alert level is the input other people plan around. It is what an emergency manager checks, what an airline dispatcher checks, what a shipping operator checks. Normal means somebody looked and the volcano is behaving. Unassigned means the question was not answerable. Those two produce very different responses from a careful reader, and exactly the same response, none, from a busy one. These are not obscure geological curiosities either. Anatahan erupted explosively in 2003 in a substantial eruption that put ash into the regional airspace and required the island to remain evacuated. Pagan has a history of significant eruptions, including one that forced the evacuation of the people who lived there, and the island has never been fully resettled since. Agrigan is one of the tallest peaks in the entire Mariana chain, a stratovolcano rising thousands of feet out of the ocean. Maug is the remnant rim of a drowned caldera, 3 islands that are the surviving edges of something much larger that collapsed. These are real, active, hazardous volcanoes in United States territory, and the official position on all 10 of them is that nobody is in a position to say what they are doing. And look who is third on that list, Farallon de Pajaros. That is the island 18 kilometers from Ahyi Seamount. That is the island the NOAA divers were working off in 2014 when they heard the explosions. It is an active volcano in its own right, the local name for it, Uracas, and the older mariner's name, Farallon de Pajaros, both attached to something that has been erupting within historical memory, and mariners crossing that stretch of ocean in the age of sail used it as a landmark precisely because it was frequently glowing. It has no monitoring at all. Its alert level is unassigned. So the geography of this corner of the Pacific looks like this. There is a submarine volcano at 55 meters depth, currently at advisory, monitored by a microphone 1,400 miles away. 11 miles from it there is a subaerial volcano with no alert level, because there is nothing on it, and spread through the chain to the south are 8 more in the same condition. This is the point where the story stops being about Ahyi. I have spent this entire video describing Ahyi's monitoring gap as if it were a specific problem with a specific volcano, and that framing has been useful but it is not accurate. Ahyi is not the exception in this arc. Ahyi is the best case. It is the one volcano in this stretch of American territory that gets a weekly paragraph, a color code, and an alert level. And it gets those things not because it is well instrumented, but because it happens to sit in water that carries its voice to an atoll that happens to be listening. The other 10 do not even get that. They get a sentence explaining why they cannot be assessed, which reframes the question this whole video has been circling. I have been asking whether anyone would know if Ahyi Seamount were erupting right now. The larger question, the one that the list at the bottom of the bulletin forces, is how much of the volcanic activity in the American Pacific is simply not being observed at all, not misinterpreted, not underreported, but never detected in the first place. There is no way to answer that. By definition, the things you never detect do not appear in your catalogue of things you detected. And the reason any of this matters, the reason a remote shallow volcano with no neighbours deserves this much attention rather than a footnote, comes down to what a mountain like this is physically capable of doing on a bad day. We have a very recent, very well documented example. It happened 4 years ago, in water not unlike this, at a volcano not unlike this, and it rewrote what everyone thought shallow submarine systems could do. Part 12. The Worked Example. On the 15th of January 2022, the Hunga Tonga Hunga Ha'apai volcano erupted in the South Pacific. Before that morning, Hunga was a fairly unremarkable entry in the global volcano catalogue. It was a submarine volcano with a small island poking above the surface in the Tonga archipelago, which had gone through some modest eruptive activity in the preceding weeks. Enough to be noted, not enough to alarm anyone outside the specialist community. The vent sat at a depth on the order of 150 metres. That preceding activity is worth pausing on, because it is the closest thing to a warning that anybody got. Through late December of 2021 and into the first days of January, Hunga had been putting up ash plumes and building new land above the waterline. It was behaving the way shallow submarine volcanoes in that region behave, which is to say noticeably, but not alarmingly. Then, in the days before the climax, the activity appeared to ease off. Anyone watching would have reasonably concluded the episode was tapering. Then it did something that the models did not have a slot for. The explosion has been assessed as possibly equivalent to a volcanic explosivity index of 5 and described in the scientific literature as the largest seaborne eruption in nearly 1.5 centuries, the first thing of that class since Krakatau in 1883. Estimates of the explosive energy, derived from waveform analysis, span a range from 1 megaton to 90 megatons of TNT equivalent, with roughly 25 megatons cited as a suitable central figure. That spread tells you something about how difficult the event was to characterize even with the entire modern global monitoring apparatus pointed at it. 25 megatons is well over 1,000 times the Hiroshima yield. The eruption column punched into the mesosphere. Let me be specific about what that means, because volcanic plumes are usually described as reaching the stratosphere, and that is already extraordinary. The mesosphere is the layer above that, the region where meteors burn up. An eruption plume does not simply drift to that altitude. It is thrown there by an explosion at sea level, pushing a column of ash, steam, and rock upward through the entire depth of the weather-bearing atmosphere and out the other side. That plume was electrically alive in a way nobody had recorded before. The interaction of ash, ice, and water in the column generated lightning at a rate that dwarfed anything in the observational record for a thunderstorm, a continuous barrage of discharge inside the eruption cloud, imaged from orbit for hours. Then, the pressure wave. The explosion launched an atmospheric wave that swept outward across the entire planet. Barometers in Europe and North America registered the pulse as it passed over, then registered it again as it came back around from the other side, and again after that. The wave circled the Earth multiple times before it faded below the noise. People in Alaska, nearly 10,000 kilometers away, heard the sound of a volcano in Tonga as a series of distant booms, and then there was the water. The tsunami produced peak run-ups of approximately 19 meters in western Tongatapu, approximately 20 meters on the southeastern side of Nomuka Iki, and approximately 20 meters on southern Tofua. 20 meters is a 6-story building. That was the height the water reached above sea level as it came ashore, generated by a volcano that had been sitting quietly under 150 meters of ocean. The consequences did not stay local. Waves from the eruption reached coastlines around the entire Pacific Rim, and people died on the far side of the ocean in South America, where the surge came ashore on beaches thousands of kilometers from Tonga, with no warning that would have connected it to a volcano nobody there had heard of. Meanwhile, Tonga itself went dark. Ash blanketed Tongatapu, contaminating water supplies and grounding the flights that would have brought help. The single undersea fibre optic cable connecting the country to the global network was severed by the event, and communication with the outside world collapsed for days. The world's first clear look at what had happened to the islands came from satellites and from an aircraft flying survey passes, not from anybody on the ground. When ships and survey teams eventually got out there to look at what was left, the mountain had rearranged itself. The island that had existed above the waterline before that morning was, for practical purposes, gone, reduced to scraps of its former outline. The summit region of the volcano had been excavated to a depth far below where it had stood. An enormous volume of the edifice had been removed from where it was and redistributed across the surrounding seafloor as debris. That is worth holding on to because it is the clearest available answer to a question people reasonably ask about submarine volcanoes. Where does all that energy go? At Hunga, a substantial fraction of it went into physically dismantling the top of the mountain and throwing it outward. And there is one more part of Hunga's history that maps onto this story with uncomfortable precision. Hunga did not arrive at January 2022 as a stable feature. In the years beforehand, it had been building. Eruptive episodes in the preceding decade had piled fresh material above the waterline, at one point joining what had been 2 separate islets into a single connected landmass. It had been growing, episode by episode, in exactly the manner that submarine volcanoes grow, adding fragmented material to the top of the pile, raising the summit region, reducing the depth of water over the vent. In other words, before Hunga did the thing nobody expected, it spent years doing the thing Ahyi is doing now. I do not want to push that parallel further than it will bear. Hunga was a caldera system with a very different plumbing arrangement, and its climactic eruption drew on a magma body of a scale nobody has any evidence for beneath Ahyi. Growth is not a countdown. Plenty of submarine volcanoes build themselves upward for centuries and never do anything more dramatic than make a new shoal. But the sequence, a shallow submarine volcano with a modest catalogue entry, quietly raising its summit through successive episodes, then a climax that the scientific community had not considered to be within that class of volcanoes' range, is now a documented pathway rather than a hypothetical one. It happened once, 4 years ago, in this ocean. Now I want to be careful and precise about why I'm telling you this, because there is a lazy version of this comparison, and it is not the one I am making. I am not telling you Ahyi Seamount is going to do what Hunga did. Hunga was an enormous event with a specific magmatic setup, an enormous volume, and a caldera structure that Ahyi is not known to share. The overwhelmingly likely future for Ahyi is more of what it has already been doing. Periods of effusive activity and gas venting that stain the water and stop. What Hunga established is narrower and more important than a prediction. It established a proof of concept. Before January 2022, the working assumption across a lot of the field was that shallow submarine volcanoes had a ceiling. Water suppresses explosivity, water quenches magma, water absorbs energy. A submarine system might be locally dangerous, but the truly catastrophic explosive events were the business of large sub-aerial volcanoes with long repose intervals and well-studied calderas. Hunga demolished that assumption in about 11 minutes. A shallow submarine volcano with a modest recent history produced one of the most energetic events of the modern instrumental era and a tsunami that killed people across an ocean basin. It also demonstrated that the water, at the right depth and the right mixing ratio, is not only a suppressant, it is a participant. The energy released when seawater and magma interact at those scales appears to have added to the explosion rather than damping it, which is exactly the inversion of the intuition everybody starts with. And the second thing Hunga established is the one that matters most for everything I have been describing. Hunga was, by the standards of this conversation, well observed. It was in a monitored region. It had shown precursory activity for weeks. It was being watched by regional agencies, imaged by satellites, and it sat within reach of the global seismic and hydroacoustic networks. Tonga had a functioning tsunami warning arrangement. None of that produced meaningful advance warning of the climactic event. The eruption escalated on a timescale that outran the ability of the observing system to interpret what it was seeing and issue a warning that would have changed outcomes. The activity had appeared to be easing in the days beforehand, which is the worst possible thing for a monitoring system to be telling you shortly before the largest explosion in a century and a half. So when I say that Ahyi Seamount has no local instrumentation and cannot be forecast, hold that against the fact that Hunga had far more than Ahyi has and was still functionally a surprise. That is the honest shape of the comparison. Not Ahyi will do this. Rather, the best-case version of this scenario, at a volcano with real monitoring and prior warning signs, still arrived faster than anyone could act on it. And the tsunami at Hunga was not generated by one process. It was generated by 4, running in combination, and 2 of those 4 are mechanisms that a mountain like Ahyi possesses right now. Part 13. The 4 ways water moves. When researchers went back through the Hunga event to work out what had actually generated the tsunami, they did not find a single mechanism. They found that a combination was responsible, and the combination had 4 components. I want to walk each one, because each one maps onto Ahyi Seamount differently, and the differences are the whole point. The first mechanism is the eruption itself displacing the sea surface. A sufficiently violent explosion at shallow depth shoves an enormous volume of water upward and outward. The water column above the vent is physically thrown, and what goes up comes down and propagates away as a wave. This is the most intuitive of the 4 and the one people picture when they imagine a volcanic tsunami. Does Ahyi have this mechanism available? Yes, in principle. It sits at 55 meters, which is well inside the depth regime where explosive fragmentation is possible, and the survey has explicitly flagged the potential for activity to breach the ocean surface. The scale would be nothing like Hunga, but the mechanism is not hypothetical. The second mechanism is flank failure, submarine landslides around the edifice. A mass of the volcano's flank detaches and runs downslope, and the water above it and around it has to go somewhere. Landslide-generated waves behave differently from earthquake-generated ones, and the difference is worth understanding. An earthquake tsunami lifts a very wide area of seafloor by a modest amount, producing a wave with an enormous wavelength that crosses oceans efficiently. A landslide displaces a smaller area violently, producing a steeper, shorter wave. Close to the source, that can be dramatically higher than anything a comparable earthquake would generate. The largest wave run-ups ever recorded anywhere were produced by landslides into water, not by earthquakes. The trade-off is that short-wavelength waves lose energy as they spread far more quickly. A landslide tsunami is a local weapon. It is devastating within tens of kilometers and often unremarkable 1,000 kilometers away. Does Ahyi have this mechanism available? This is the one with a name and a location. In 2014, a large landslide chute developed on Ahyi's southeast flank. That is not a modelled possibility. It is a documented event that already happened at this specific volcano on that specific side, leaving a specific scar. 3 eruptive episodes have loaded the edifice since, and nobody has surveyed it to establish its current condition. Of the 4 mechanisms, this is the one where Ahyi has already demonstrated the capability. The third mechanism is caldera collapse, the summit region foundering into a magma chamber that the eruption has emptied. The roof loses its support and drops, and the sea rushes into the void and then back out. It is a 2-stage wave, a drawdown as the water pours in, then a surge as it rebounds. Does Ahyi have this mechanism available? Unclear, and honestly unlikely at the scale that mattered at Hunga. Ahyi is described as a conical edifice rather than a caldera system, and the collapse mechanism requires a shallow chamber of substantial volume that empties fast enough for its roof to fail. This one I would put in the possible but not indicated column. The fourth mechanism is the strangest, and the one that surprised people most: meteor tsunami, generated by atmospheric gravity waves. The pressure pulse from the Hunger explosion travelled through the atmosphere and coupled with the ocean surface as it went, pushing the sea ahead of it and generating waves that arrived at coastlines around the world ahead of the conventional tsunami. Tide gauges in ocean basins that have no water connection to the South Pacific recorded a signal from an eruption in Tonga, because the signal had travelled through the air and stepped back into the water on the other side. Does Ahyi have this mechanism available? Only in the scenario where it produces an atmospheric explosion of a scale nobody is forecasting. Set this one aside. So of Hunger's 4 pathways, Ahyi credibly holds 2, and one of those 2 it has already used. Now the part that ties this back to everything else, and it is about time rather than mechanism. Tsunami warning systems, the ones that actually work and have saved lives, are built around earthquakes. The reason they work is a quirk of physics. Seismic waves travel through rock at several kilometers per second. A tsunami in deep ocean travels at a speed set by the depth of the water, roughly the square root of gravity times depth, which in 4 kilometers of open Pacific works out to around 200 meters per second. That is about 700 kilometers an hour, the cruising speed of a passenger jet, which sounds terrifyingly fast until you compare it to the alternative. Seismic energy from the same event is already at the far side of the ocean before the wave has cleared the horizon. That gap, minutes for a near source, many hours for a distant one, is the entire basis of tsunami warning. You detect the earthquake, you characterize it, you compute, you warn, and the wave arrives afterward. Then a network of pressure sensors on the deep sea floor confirms whether a wave is genuinely propagating, which is what turns a computed forecast into a confirmed one. Notice what every piece of that chain assumes. It assumes an energetic seismic signal that arrives early. It assumes instruments positioned to catch it. It assumes sensors in the water along the path. A volcanic tsunami from an uninstrumented source inverts that advantage completely. If Ahyi's southeast flank fails, there is no seismic precursor racing ahead through rock to a network that is watching for it. A landslide is a poor generator of the sharp, high-frequency energy that seismic networks key on. It is a mass sliding, not a fault snapping. What there is instead is a mass of debris moving downslope underwater. The acoustic signature of that will reach Wake Island, eventually, 25 minutes later, and it will be analysed eventually, and somebody will conclude that something happened at or near Ahyi Seamount. That conclusion will arrive after the wave has already done whatever it was going to do. The deep ocean pressure buoys that anchor Pacific tsunami detection would help, but they are spread thinly across an ocean that covers a third of the planet, and what they detect is a wave that is already travelling. They are confirmation instruments, not warning instruments, for a source this close and this quiet. Run the sequence forward, and it is bleak in a very ordinary way. At some minute on some day, a section of the southeast flank lets go. Nobody is watching, because there is nothing there to watch with. The mass accelerates downslope and the water above it is displaced, and a wave leaves the volcano in every direction at once. Within a minute or 2 it has reached the water directly overhead, where any vessel working the ground finds out about the eruption by being lifted. Within a few minutes more it is at Farallon de Pajaros, 11 miles away. 25 minutes after the failure, the sound of it arrives at Wake Island, and is recorded and sits in a data stream alongside everything else the Pacific was doing that day. At some later point, hours, more likely days, an analyst working through that stream notices a signal, characterizes it, cross-references the seismic records from Guam and Chichijima, and establishes that something occurred at or near Ahyi Seamount. A satellite pass, weather permitting, might show discolored water. A bulletin is written. It is accurate, careful, and entirely retrospective. At no point in that sequence does anybody get told anything before it happens. The chain is not slow because people are slow. It is retrospective by construction, because every instrument in it is somewhere else. For a source this remote, in a region this sparsely populated, the practical consequences are limited, and I want to be straight with you about that rather than inflating it. The northern Marianas are largely uninhabited at that end of the chain. Farallon de Pajaros, 18 kilometers away, has no permanent population. The populated islands, Saipan, Tinian, Rota, are several hundred kilometers south, and Guam beyond them. Given how quickly a short-wavelength landslide wave loses height with distance, a local flank failure at Ahyi is not a credible threat to those southern islands. But limited is not zero, and there is a category of people for whom the distance is not several hundred kilometres. It is zero. There are fishing vessels and cargo traffic in those waters, with no exclusion zone and no marked hazard. There are research teams who work off Farallon de Pajaros, as the 2014 divers were. And the survey's own hazard statement is not about distant coastlines at all. It is about the water directly above the volcano. Eruptive activity at Ahyi Seamount may present a hazard to mariners in the water above and near the volcano. That is the sentence that ties the whole hazard back to the whole monitoring gap. The people at risk are the ones directly overhead, and the mechanism by which they would be warned does not exist. Every one of these mechanisms, if it fires, will be detected by a microphone 1,400 miles east, some time after the fact. Which returns us to the stain on the water, and to the only question that has actually mattered from the beginning. Part 14. What is under there right now? I open this with a satellite image from the 11th of July 2026, showing 200 metres of discoloured water in the Western Pacific. I want to end by telling you exactly what we know about that patch of ocean today, on the 14th of August, and exactly what we do not. We know that between late June and the middle of July, something beneath it was venting gas vigorously enough and persistently enough to stain the surface across multiple satellite passes. We know that on the 16th of July, the United States Geological Survey judged that sufficient to raise the alert level to advisory and the aviation colour code to yellow. We know they described the cause as either vigorous hydrothermal degassing or an ongoing effusive eruption, and declined to choose between them. We know they stated it indicated increased volcanic unrest and potential for activity to breach the ocean surface. We know that since the beginning of August, 2 consecutive weekly bulletins have reported nothing. No plumes, no acoustic detections, clean water in the images that were clear enough to use. We know that the alert level has not been lowered, and we know that the survey's standing description of this volcano's history still reads that the most recent eruptive activity began in 2022, with no closing date, 4 years on. What we do not know is whether Ahyi Seamount is erupting, not because the evidence is contradictory, because there is no evidence that would settle it. A volcano that has gone quiet, and a volcano that is quietly effusing lava at 55 metres depth, produce precisely the same observations from the instruments that exist. Nothing on an occasional clear satellite image, nothing on a distant array that is available when it is available. Both worlds generate this morning's bulletin, word for word. I promised earlier that I would come back to the theories, and this is the right place to do it, because they cluster around exactly this gap. The most common one is the simplest. They are hiding an eruption. The alert level says one thing, the observation report says another, and to a lot of people that reads as an agency saying something, it does not mean while sitting on what it does. I understand the instinct. But the evidence points hard the other way. An organisation concealing volcanic activity does not publish a weekly document stating plainly that it saw nothing, and it certainly does not volunteer in the same document that it is unable to forecast or warn of impending eruptions. That sentence is the single most damaging admission the survey could make about its own capability, and it prints it, unprompted, every week, for a volcano almost nobody is reading about. The more sophisticated version fixes on Wake Island, and it goes like this. The detections come from an atoll with a military history. The acoustic infrastructure out there has a lineage in submarine and nuclear test surveillance. Therefore the real data is classified, and what the public gets is a filtered version. The factual kernel is real, and I said so earlier, that heritage is genuine, and the physics of hearing a volcano across an ocean is the physics of hearing anything else across an ocean. But the conclusion does not survive contact with the record. The Wake Island detections are not hidden. They are precisely what the survey cites publicly, with dates, with clock times to the minute, with the international collaboration named. If the arrangement were about concealment, the bulletins would not be built on it. And the third theory, that undersea volcanoes are erupting more often than they used to, I have already dealt with in the honest way. What has increased is our capacity to hear them, and a graph of detections is not a graph of eruptions. What I keep landing on is that the version of this story without any conspiracy in it is worse than the conspiratorial version, not better. A cover-up implies someone knows. The published, acknowledged, Restated gap implies nobody does. There is a version of this story that ends with reassurance, and I am not going to give it to you because it would not be true. There is also a version that ends with alarm, and that would not be true either. Ahyi has been doing roughly this for 47 years, and the most probable outcome by a wide margin is that it continues doing roughly this, and the alert level quietly returns to normal in some Friday bulletin that nobody reads. What is left, when you take away both the reassurance and the alarm, is something I find harder to sit with than either. There is an active volcano in United States territory. Its summit is 55 meters below the surface of the Pacific, and it has been building itself upward toward that surface, eruption by eruption, for as long as anyone has been keeping track. One side of it collapsed in 2014 and has been reloaded 3 times since, and nobody has been back to measure it. Its behaviour has been established across half a century by a fishing crew who felt the deck shake, a seismic station 7,000 kilometres away in French Polynesia, a team of divers who happened to be in the water, and a microphone on a coral atoll 1,400 miles to the east. And every Friday, an American government agency publishes a document about it that contains the sentence, "The lack of local real-time data means we are unable to forecast or warn of impending eruptions." Nobody is hiding that. That is the thing I keep coming back to. The gap is published. It is restated, without prompting, week after week, by the people whose job it would be to close it if closing it had ever been funded. The most unsettling document in this entire story is a routine bulletin that says, in effect, here is what we can see, here is what we cannot, and we would like you to understand the difference. And the frustrating part, the part that makes this a story about a decision rather than a story about the limits of science, is how small the fix is. One ocean bottom seismometer on that edifice would hear the volcano's own earthquakes, in the ground, as they happen. It would distinguish between a hydrothermal system circulating and magma-breaking rock on its way up, which is the exact distinction the survey has been unable to make since July. A moored pressure sensor above the summit would register the gas flux directly, instead of inferring it from a stain that only exists when the ocean is calm and the sky is clear. One survey ship, on one transit, could map that southeast flank and tell us whether the scar from 2014 has been buried, steepened, or left alone. None of that is research at the edge of what is possible. It is standard equipment, routinely deployed, on a mountain nobody has prioritized. And I want to be fair about why. Every monitoring budget in the world is a ranking exercise, and the ranking is done by consequence. There are volcanoes on this planet with cities on their flanks and millions of people inside the run-out distance of a single flow. Against that, a submarine seamount in an almost unpopulated stretch of the Northern Marianas is an entirely reasonable thing to leave at the bottom of a list. Nobody made a stupid decision here. A sequence of defensible decisions produced an indefensible situation, which is how most of these situations get produced. But it does mean that the honest answer to the question I have been circling is not a fact about the volcano. It is a fact about us. There are exactly 3 things that would move this story, and I want to name them, because they are checkable, and I would rather leave you with something to watch than with a mood. The first is the weekly bulletin. If Ahyi is moved to normal and green, the survey has concluded the 2026 episode is over, and given how it words these things, quite possibly that the sentence which has been open since 2022 can finally be closed. The second is a survey ship. If anybody publishes a fresh bathymetric map of that southeast flank, we will know for the first time in 12 years whether the scar from 2014 has been reloaded, and by how much. That single data set would convert the most credible hazard at this volcano from a plausible mechanism into a measured quantity. The third is an instrument. Any proposal, any funding line, any deployment that puts a seismometer or a pressure sensor on or above that mountain would end the condition this entire story describes. Its continued absence from the next budget cycle is the quiet confirmation that the gap stays. Everything we know about this mountain, we overheard. So the thing to watch for is not a plume and not a wave. It is a paragraph. Next Friday, the Northern Mariana Islands Weekly Update will publish again, and Ahyi Seamount will either be moved down to normal and green, or it will be held at advisory and yellow for another week with nothing to show for it. Those 2 outcomes look almost identical on the page. They mean entirely different things. One is an agency saying the episode is over, the other is an agency saying for the 5th week running that it cannot tell about a volcano that has now been officially erupting without interruption or conclusion since 2022. Which one appears is going to tell us less about the volcano than about how much anybody can actually see down there.